Hello students, in today's video we are going to learn how R.A. Millikan determined the charge on the electrons with the help of oil drop experiment. It took him nearly 8 years from 1906 to 1914 to perform this experiment. In my previous video, I taught you how Sir J.J. Thomson calculated the charge to mass ratio of electrons. If you haven't seen that video, please follow the link given in my description box. So let's start. R.A. Millikan had this kind of an apparatus. This is a chamber, an atomizer is there, viewing telescope, X-ray source, light source, 2 plates. The upper plate has got a tiny hole inside and a high voltage supply. Now this atomizer has got oil inside. The function of the atomizer is to spray the oil in the form of tiny oil droplets. Now mind it, when these oil droplets fall down after being sprayed, they occupy spherical shape. As we know that liquid, when they fall down, they tend to occupy minimum surface area because of surface tension, and that is possible by occupying spherical shape. So they fall down occupying spherical shape. Initially, R.A. Millikan had used water, but water was more prone to evaporation and it could not retain its mass and volume, and therefore he replaced water with oil and found better and consistent results using oil. This viewing telescope was used to keep an eye over this falling oil droplets. The inside chamber was illuminated with light source. X-ray source was used to ionize the air inside and to make this falling oil droplets negatively charged. And of course there is a high voltage supply. Now initially, the first part of this experiment, R.A. Millikan did not switch on the circuit. That is, the 2 plates were electrically neutral. Okay, so when the atomizer was used to spray the oil droplets, they fell down through this, they passed through this hole and started falling down as they were continuously attracted downwards because of the force of gravity. Now when they were falling down, another force which was acting upon these oil droplets opposite to the direction of this force of gravity was the viscous drag force, which acts opposite to the relative motion of these particles. So if this is the oil droplet, the force of gravity, that is Fg, acts in the downward direction and the viscous drag force acts in the upward direction. Now, because of the viscous drag force, these oil droplets are slowed down until they reach the terminal velocity. Now, when they reach the terminal velocity, they fall down after that with a constant velocity, that is, they are no longer accelerated. So, what happens is that after attaining terminal velocity, they falls with a constant velocity. Now, what is terminal velocity? Terminal velocity. As you can see, this is the viewing telescope which was used by R.A. Millikan. With the help of this viewing telescope, he was keeping eye on this falling oil droplets. Now he measured the distance covered by this oil droplets and the time taken to cover that distance, and by doing so he could calculate the terminal velocity, which is equal to the distance covered by time taken. Now once they attain the terminal velocity, the oil droplets are no longer accelerated, that is, the acceleration is equal to 0. And from Newton's second law of motion, we know that force is equal to mass into acceleration. Now, since acceleration is equal to 0, so we can write force is equal to mass into 0, which ultimately becomes equal to be 0. So, after they attain the terminal velocity, the particles do not experience any kind of force. Or we can say that the force of gravity is being equally balanced by the viscous drag force, which is acting opposite to the direction of the force of gravity. Thus, we can write viscous drag force to be equal to force of gravity. Now, what is viscous drag force? The formula for viscous drag force is 6 pi eta r into V. This eta is the viscosity of the fluid through which the oil droplets are falling down. Now, the fluid is air in this case, and the viscosity of air is a known value. R is the radius of the falling oil droplets because they occupy a spherical shape, and V is the terminal velocity as discussed earlier. Now, what is force of gravity? Force of gravity is equal to mass of this oil droplet multiplied with the acceleration due to gravity. Now, acceleration due to gravity's value is known to us, 9.8 meter per second square. And for the value of mass, we have the equation density is equal to mass per unit volume. Now, density can be written as rho is equal to, for mass, m, and for volume, v. This implies that mass is equal to rho into v. Now, this v is for the volume, and volume of the oil droplets is equal to volume of sphere, which is equal to 4 by 3 pi r cube. This r is the radius of this spherical oil droplet. So we can write the value of mass to be equal to 4 by 3 pi r cube into rho. Thus, mg becomes 4 by 3 pi r cube to rho g. This equation Fv is equal to Fg, let this be equation 1. Now we will try to put the value of this one, which is force of gravity, in equation 1, and we will try to put the value of the viscous drag force in equation 1, and then we will equate both the things. So we can write the viscous drag force, that is 6 pi eta r into v, is equal to 4 by 3 pi r cube rho into g. Now pi can be cancelled out because it is there in both the sides of the equation. R comes to be equal to r square because r and r cube can cancel, and we can write r square over here. So ultimately we can write the equation for r squared to be equal to 9 by 2 eta v divided by rho into g. Thus v is the terminal velocity, eta is a known value, density is also known, and this g, that is acceleration due to gravity, is also known. Now this is the value of r square. From the known values, the unknown value can be calculated. That is, implies that r is equal to root over 9 by 2 eta v by rho into g. This value will be utilized later on, okay? Now, Let us move to the next part of the experiment. In the next part, Millikan switched on the circuit in such a way that the upper plate was connected to the positive terminal and the lower plate to the negative terminal. So the upper plate became positively charged and the lower plate became negatively charged. Now when this oil droplets pass through this hole, at the same time these oil droplets are being negatively charged up with the help of this X-ray source. So what happens is that these oil droplets are being attracted by this positively charged plate. We can say that an electrical force acts upon this oil droplets. And at the same time, one more force is that acts upon these oil droplets is the force of gravity, which is trying to pull these oil droplets downwards. Now what R. Millikan did, he tried to balance both the forces in such a way that these oil droplets become stationary at a point. Now when these oil droplets become stationary, they will not undergo any kind of force upon them, viscous drag force upon them, because viscous drag force acts opposite to the direction of relative motion. As there is no motion, so no viscous drag force. And because they are stationary, therefore we can say that the electrical force which is acting upwards, let me make you understand with the help of another diagram. If this is the spherical oil droplet, this is the normal force of gravity acting downwards, and in this case the force which is acting upwards is the electrical force. And when these oil droplets are stationary, because we are able to balance both the forces, that time electrical force becomes equal to the force of gravity. Now the force of gravity is known to us because we calculated just now. Force of gravity is mg is equal to 4/3 pi r cube rho g. And talking about the electrical force, this has got the equation electrical force is equal to Q into E, where Q is the charge and E is the electrical field. Now electrical field's value will be known to us because we are adjusting the electrical field. The only unknown value is the charge. Also, the electrical field E can be written as voltage supplied between the two plates, in this case between the two plates, divided by the distance between the plates. The voltage can be written as V divided by T. So E comes out to be V divided by C. So we can write V divided by D. So we can write the electrical force to be equal to Q into V by T. Now we will be putting this value of electrical force in this equation 2. So what do we get? We get Q V by T to be equal to 4/3 pi r cube rho g. Here you can see that the value of r cube is required, and we had calculated the value of r. So from here we can calculate the value of r cube. So let me write a note over here that r cube will be equal to the cube of this quantity, which will be equal to 9/2 eta V divided by rho g to the power 3/2. So I can write Q to be equal to 4/3 pi r cube rho g. This t will move upside and V will come down. So the value of the charge can be calculated this way. Mind it, charge is the only unknown quantity. 4/3 is a constant. Pi's value is known to us. R cube's value can be calculated. Rho is the density of the oil droplets which is known to us. G is acceleration due to gravity, which is also known to us. The value of the distance between the plates is known to us, and this is the value of the voltage, which is also known to us. So the only unknown value can be calculated, and Millikan calculated the value of Q by performing and repeating the experiments again and again. And every time he found the value of Q to be Q was always a multiple of 1.6 into 10 to the power minus 19 coulomb. So he concluded that 1.6 into 10 to the power minus 19 coulomb must be the basic, or you can say fundamental charge. And this is the charge on the electron. Hope this video was useful to you. So please like the video, please share the video, and do subscribe to my channel if you haven't subscribed yet. And do not forget to press the bell icon. Thank you, dear students.